Hi, I'm Gilliam. I'm the sub-team lead for the payload part of the Lunar project, Senior Design Team project. This project is one to compete in the Argonia Cup competition in Kansas. It's a collegiate level competition where teams build solid fuel rockets that need to reach a minimum altitude of 9,000 feet. And then on the way back down, the rockets deploy some form of payload that will deliver a golf ball to a target location. I'm the payload sub-team lead, and then this is Jared. He's the electrical team lead for the payload part of the project. And we're just gonna be showing you around the lab today and the different facilities that are available for us for this project. So over here, we've got our soldering station with a microscope. This allows us to do a lot of really cool micro soldering stuff for the drone. We primarily use it for repairing broken electronics that we damaged through the course of testing our drone. We also have a vacuum chamber over here that's been super useful for testing the avionics bay of the rocket. We can simulate different altitude conditions by pulling different levels of vacuum, and we can use that to validate our electronics before we send our rocket up. And then let me move the camera over here. So then over here, we've got this table. This is where we work on most of the actual frame of the drone. We've decided to 3D print most parts of the drone just because that allows us to rapidly prototype and make large design changes without having giant manufacturing lead times. So as you can see, there's a lot of drone parts over here because we're in the middle of a pretty big design revision. And having access to this lab is super helpful for the project because this lab is dedicated to this project and this project alone, which means that we can come in here whenever we want and we have all of the resources we need to work on the project in this lab, so we don't have to schedule lab times at another location. So then to just talk a little bit about the actual drone, it has to fit inside of a 4-inch rocket so that it can reach our target altitude of 18,000 feet. So the arms fold down like this, and then once it's deployed from the rocket, it actually gets fired out by a black powder charge. And then the arms are gonna unfold on their own, and the drone will arm, and it'll fly back to the target location autonomously. So this drone needs to fly about 5 miles, as that's about how far our rocket is targeted to drift. So that's a pretty strenuous requirement on a drone that has to fold up. So we've had to increase the size of the drone this year just so we can hit that target range of 5 miles. I'm now gonna turn it over to Jared to talk a little bit about the electrical subsystems and the radio control system for the drone.
Yeah, so we got two things aside from the drone here. We've got our controller, and then we also have a first-person viewing headset. And this first-person viewing headset has 2 antennas on it. One is directional and has really high gain. So if you point it at the drone, we pretty much get a signal whenever we want. And then we've got this omnidirectional one, which cuts out really quickly, within a few hundred meters, but it doesn't have to be pointed at the drone. And the big challenge for me on this project is to try and figure out how to have communication with the drone, both in video and telemetry and like control signals 5 miles away, because that's how far we can fly the drone. So we want to be able to be in communication with it the whole time.
Yeah, so this is just one of the really cool projects that LeTourneau has available for students to work on for their senior design project. And this is one of many labs we have dedicated to those projects. And it's really cool to have a lab solely dedicated to this project.